I will see some of you maybe tomorrow in fluids.
And
I will
Thursday.
be seeing some of you Thursday in vibrations. Vibrations is the toughest one, by the way, you know? So it's not gonna be an easy term, you know? It's gonna require a lot of work, and particularly in vibration fluids, it's okay, I think. Since I changed the textbook, I think it's much nicer, much easier. But this one shouldn't be a problem, right? But vibration is the one that is probably going to be a bit challenging, you know, particularly if you want to make it easy for you. I shouldn't be talking about vibration right now, but if you want to make it easy for you, please spend some time and look at on how we solve differential equations, first order, second order particularly. You know, just to kind of get an idea of how things go. Okay, so welcome to the ride. So it's gonna be.
Week 4 and week 7 are gonna be
Oh my God!
brutal.
Are you even stagger that just a little
Don't
bit?
remind me.
It's more my
We're on the receiving end.
You guys are the receiving end. Yeah, that's
I
true.
mean, he's got great.
Yeah, I'm gonna be busy too. I have 2 sections, by the way, of so I'm teaching kind of every day. I have Thermo on Monday, fluids on Tuesday, dynamics on Wednesday, vibration Thursday and Friday.
Alpha.
That is a rental.
Yeah.
And I'm teaching a UW class too, strength of materials. So it's going to be a busy time. All right. So let's start. So this is going to be a big review, and I think you probably will agree that it's good because you will probably notice that some of the stuff has evaporated, maybe, you know, through the holidays. But what I did is I took all those notes and then just kind of captured the important part, you know, from each one, and just have it into one little thing. So remember what we did in chapter 1? Chapter 1 in thermodynamics was basically just a review, or not a review, but an introduction, I meant to say, of some concepts. The key concepts that we learned is a system. What is a system? Is whatever you need to study. A good example of that would be, for example, in a piston cylinder, the air that is inside is the system, okay? And remember, the system would have a boundary. Everything that is outside is called the surrounding. And here and what's surrounding the system is the boundary. And there are 2 types of systems. You know, there are systems that do not involve mass coming in or going out. We call that a closed system, or control mass. Control mass because the mass does not change, right? But sometimes the system has an opening, 1 or more, and maybe exits 1 or more, okay? And we call that an open system or a control volume, okay? And that volume, the surface that it encloses that volume is called the control surface. Remember what the idea of thermodynamics is? Anyone remembers? If you need to apply it to just this system. No? Remember the big question about thermodynamics, just so you know, this system communicates with the outside through heat and work. And then knowing this and that, we should figure out what happens to the energy. That's really what thermo in a nutshell is. In other words, how does the energy here change in a system, right? If it interacts with the surrounding through a heat and work. So closed system, what is an isolated system? An isolated system is a system that does not, you know, communicate with the outside either through work or through heat. So it's a special types of system. You know, it does not interact in any way with its surroundings. Open and close, we already defined it. Examples of open systems are, you know, a pump, a heat exchanger, whatever, a turbine, a nozzle. And what else? We talked about properties. Remember, a property is a macroscopic characteristic of a system. It's just a mass, a volume. You don't need, it's whatever that value is at that particular state, which is independent of whatever it was before, okay? A numerical value can be assigned at a given without knowledge of the previous history of the system. You don't need to know, you just need to know what volume it is, what mass it is, etc. The word state refers to a system as described by properties. So remember, all these in red are some definitions. And as the system goes from one state to another, that means it has gone through a process. And steady state is another very important thing that we use in thermodynamics, which we'll use a lot in fluids, and it's called it's when none of the properties change with time, okay? In other words, any dE over dt is equal to 0. Two key things in here: intensive properties versus extensive. What is the difference? Extensive means it depends on the extent of the mass. Intensive does not depend on mass. Okay, that's all there is to it. And to be more exact, the properties that are expressed in lower cases in thermodynamics, are they extensive or intensive? Intensive. The capital ones are extensive. Classical thermodynamics, we describe the states always at equilibrium. That means equilibrium means it reached. For example, if I have a gas in a cylinder at a certain pressure, well, it is at a certain pressure, a certain temperature, right? And then let's say I add heat to it. What's going to happen at constant pressure? Maybe the volume is going to change and the temperature may change, but eventually it's going to change until it stops. That means it has reached what? Another equilibrium state. Equilibrium state is when you reach equilibrium and nothing really changes, because in that process, obviously everything is changing. So at equilibrium, temperature is uniform throughout the system, and the pressure can be regarded as that, because that's what equilibrium is all about. They are not allowing any internal changes to occur. We also talked about units, in SI, kilograms, meters, second, and Newton. And then in English, it's the pound mass, the foot, the second, and the pound force as used in here, okay, in thermo. We defined another very, very important property, which is the specific volume. Remember, I always said that fluids likes to use density, and you will see that tomorrow, right? Fluids doesn't like specific volume. It has nothing to do with it. Thermo likes that, and obviously the relationship between them is one is the reciprocal of the other, okay? Pressure is also another property, which is simply force per unit force per unit area. And pressure measurements, remember, and we will be developing this in fluids, by the way. Manometers and there's a big part of fluids is really manometer studies. How do you figure out what the pressures are, etc. So here the pressure, as long as you know whether it's the same, when it's the same fluid, it's the same kind of horizontal thing, the pressure is going to be exactly the same. And this is again how you relate the atmospheric pressure to the vapor pressure, which is almost nil, meaning that a barometer, if you know the displaced length, you can get a value of the atmospheric pressure directly. We also talked about two different kinds of pressures. There is absolute pressure and gauge pressure. What's the difference? Absolute is measured with respect to a zero reference, whereas gauge is with respect to atmospheric pressure. Lastly, we talked about temperatures. In SI, we use the degree C and Kelvin, right? The relationship between them is here. And in FPS units, or English units, it's the Fahrenheit and the Rankine, okay? And this is the relationship. A lot of people use 460 instead of 490, 459.67, you know, 5 significant figures, not gonna do you much. Okay, and the relationship obviously between Celsius and Fahrenheit is this relationship. So you can navigate between the temperature scale very easily, and this one is just a scale showing the different temperatures with the steam point and the ice point as references. We know them in SI as 0 degrees and 100 degrees, right? Which corresponds to 32 degrees and 212, you know, the boiling and the freezing temperatures. That's what we did in chapter 1, in a nutshell. So, after we covered all those, then we moved on to chapter number 2. Anyone remembers what we did in chapter 2? It's obviously energy, the first law of thermodynamics, which says that Q minus W is equal to delta E. So we went ahead and said, okay, since that's what we want to develop, we needed to look at each one of those terms, okay? So, and remember what the idea is, as we exchange Q and W, we want to find out how the energy changes, and that's really what the crux of the class is all about. So we talked about the energy, and we said, well, what kind of energies are we talking about? There is work. Remember, work is force times distance. And there is one theorem that is important, which is called the work energy theorem. And work is simply equal to the change in kinetic energy. And I always gave an example of a car that is traveling at a certain velocity, and then you apply the brakes. So the force, if the car is moving in this direction, the force is pointing the other way, so the work is negative. That means it is sucking up, you know, it's reducing the kinetic energy, whereas as opposed to applying the throttle, right, and adding positive work in which your kinetic energy actually increases. So work is force times distance. The units obviously is the Newton meter, and the derivative unit, that's the joule. The joule means is 1 Newton meter, or the foot pound, which is also another derivative unit associated with that is the BTU. Now, and then we said, well, in thermo, we understand how we calculate work when we study dynamics, for example, because we can visually see the force, we can visually see the distance. But if you're talking about air in a piston cylinder, what the heck is the force? What the heck is the distance? So you don't see that. That's why in thermodynamics we had to have a separate definition of work. And we call this work, that work is done on a system, on its surroundings, if the sole effect on everything external to the system could have been the raising of a weight. What are they doing back there? Testing. All right. So could have been the raising of a weight. Again, sign conventions, very, very important. When the work is done on the surrounding, the work is positive. When you are doing work on the system, the work is negative, right? And remember, for heat, it's the opposite. So we talked about energy, and then we said, okay, now let's talk about power. If energy is force times distance, that means that power is force times velocity, right? Because you're just dividing work per unit time, right? So the SI unit of power is the joule per second, aka the watt, right? Or the BTU per hour. One of the key equations in thermodynamics, remember, I always kept saying the integral of PDV. See how many times, looking back, how many times you use that equation, right? Many, many times. So how do we go from this? We derive this as being simply force times distance. The force being acting on the piston here is simply the pressure times the area, right? So PA dx P times A dx. A dx is simply the change in the volume. That's why we call this PDV. So we derived this very important equation that allows us to calculate the work done on an expanding or contracting gas. Okay? One of the containers that we refer to many times as rigid containers implies what? No work. That's the whole idea, because it's rigid. You know, the gas is not contracting and it is not being compressed, right? And therefore the work is equal to 0 in that case. So we moved on then to broadening our understanding of energy. Okay, so we talked now about work, right? Work being the integral of PDV. Then we went back and said, okay, now what is E? You know, what is the energy of the system? What makes up an energy of the system? Anyone remembers the components? It's 3 of them, right? Kinetic, potential, and anything that doesn't fit into those, it's in the basket of internal, right? Put in simple terms, kinetic and potential are mechanical energies, whereas the internal energy is more like a blank energy. It's heat, thermal energy, right? So that's what it is, potential energy, kinetic energy, and thermal energy, right? If you have those 3 baskets, you get the whole thing. So that's why you see delta E has the 3 components. Most cases, these are neglected because we are dealing with gases. You know, who cares? The mass is really small, so the kinetic energy is really not an important thing. So at least we know what makes up delta E in this case. The last one that we need to look at is Q. Remember, there are only 3 terms in the first law. We already talked about this. We already talked about delta E. Now, how about Q? What is Q? It's heat transfer. And again, that's the class that we're going to be taking next term, the heat transfer class. And we said that obviously you can, I don't know if I have it in here or not, but there are 3 modes of heat transfer that you can have. You can have heat transfer by conduction, you can have heat transfer by convection, or you can have heat transfer by radiation, okay? But either one of those, or the combination of those, will create Q. So the only way energy of a closed system can be changed are through transfer of energy by work or heat. Based on experiments of Joule and others, a fundamental aspect of energy concept is that energy is conserved. Okay? And this is what the first law of thermodynamics is, which is written as simply, so this is the relationship between the delta E that we talked about, between the Q and the W. Experiments show that when you take Q, you subtract W, following the sign conventions, obviously, right? This is what you're going to get. This is how you quantify the change in energy of the system. And a system is at steady state if none of its properties change with time. And we also talked about thermodynamic cycles. What's a change in energy of a thermodynamic cycle equal to? It's 0. Why? Because you're starting from a point and coming back to the same point. So E minus E is equal to 0. So in other words, Q cycle minus W cycle is equal to 0. That's why Q cycle is always equal to W cycle. And we have used this many times in ENGR 355. So in fact, that's what it says. At the conclusion of a cycle, all properties have the same values they had at the beginning. Consequently, over the cycle, the system experiences no net change in state. Okay, so that's what it is. And how do we show a power cycle? Remember, a power cycle gets fed what? It gets fed energy from what do we call this? How do a reservoir.
Yeah.
Remember, a reservoir is something that whether you remove heat from it or you add heat to it, its blank stays the same. Temperature stays the same. right? So this is a hot reservoir, cold reservoir, so you get fed heat from the hot reservoir. Part of it gets converted to work, and the rest of it gets lost, right? Is it possible to have, by the way, all this heat converted to all work? If it were possible, why wouldn't it be possible? Would we be violating some law? Well, conservation of energy would always work, but remember the second law of thermodynamics? There is nothing that is 100% efficient, right? So we cannot, there was always going to be losses in here. And in fact, that's probably related to the chapter that we're going to be talking about today, this exergy stuff. So this is a power cycle because it creates work, but this one create work? This one is using up work, right? That's what the refrigeration cycle does. It uses work, right? And in addition to that heat that it extracts from the cold reservoir, and then dumps everything into the hot reservoir, okay? So we'll be doing this a lot this term, in detail. Okay, power cycles, we already mentioned, and then efficiency. Remember what efficiency of a power cycle is? Is always efficiency is the output divided by input, kind of put in simple terms. So for a power cycle, what is the desired output? Is the work that you are creating, right? And then the input is the heat that you are putting into the system. So that's why you have eta is equal to W cycle divided by Q in if this is a power cycle. But if it is a refrigeration cycle, well, it depends. It depends if it's a heat pump or a refrigeration cycle. What's the difference between a heat pump and a refrigeration?
Heat pump's reversible.
Okay.
Like it'll, a heat pump,
Relative to atmosphere, right?
yeah,
No.
it'll
Isn't
pull
it
heat
true that a heat pump, this is hot, right? It still operates between, this is cold. Let's say this is the heat pump, let's say, or a refrigerator. Whether it's a heat pump or a refrigerator, you still need work, right? Work the compressor and current and stuff. And then what do? You are removing heat from here, right? Q cold, and then you're throwing everything to QH in here. Is this representation valid for both heat pump and refrigeration, or does each one have to have a different schematic? In fact,
refrigeration cycle only goes one way where a heat pump can go both ways.
right? But still, there is some truth to that. But really, the main difference is that what's the goal of? In industry, this is what they look at. A refrigeration, the goal of a refrigeration cycle is to cool a space. In other words, is how do you want to keep this one at a particular temperature? Whereas a heat pump is how much heat do you need, to heat up a space, okay? And so the representation is exactly the same, except that if you look at the COP, what does COP stand for? Why don't we call it efficiency of a refrigerator? Why do we call it coefficient of performance?
Doesn't do any work. Well, it's negative work, right?
Well, it's not right, because, I think I covered this before, because efficiency, when somebody says efficiency, what does it imply for the maximum efficiency?
100.
100, right? But this one is an output divided by the input. The output is usually much higher than the input. So, you know, to avoid that type of situation, we don't use efficiency, right? Because typically for refrigerators, you get about 3.0, 3.5 for coefficient of performance. It would be kind of weird to tell somebody, oh, it's got an efficiency of 3.5. Really? You know? So to avoid that, we say it's coefficient of performance. So for a refrigerator, for example, so remember, it's the output divided by the input, right? So what is the output, desired output here? It's QC, right? And the input is W. Whereas for a heat pump, it's going to be QH divided by W. That's the only difference, analysis-wise, you know, for a heat pump versus a, it's in the objectives, in fact. The objective of a refrigeration cycle is to refrigerate a space, right? But whereas the objective of a heat pump is to maintain the temperature higher than the surrounding temperatures. And of course, that gets transferred or that gets reflected through the coefficient of performance for a refrigerator, which is going to be different than that of a heat pump. And that's chapter number 2. So chapter number 1, really, the only thing we did was introduce some definitions, etc., right? And then in chapter 2, we went ahead and introduced the first law of thermodynamics. First law of thermodynamics, which has 1, 2, 3 quantities. We went and defined what's in here, what makes up this, what makes up that, and how are they related. And then we stopped. And then in chapter 3, we learned what? How do we evaluate properties? Chapter 3 was the big chapter, if you recall. That's when we started learning about the different phases, right, of a substance, right? If you guys remember, this is a TV diagram. We call this the dome, right? This line is called the
Saturated liquid line?
saturated liquid, and this one is the saturated vapor, and the state of the substance in here is what? If a substance is right here, is it in liquid or is it in a gas?
Some combination.
It's a combination of both, right? And if it's in here, it's liquid. If it's in here, it's just vapor. Here, it's liquid plus vapor. And there is a quantity that is important that tells us how much you have, and it's called the quality X. Okay. So we talked about those, and how many properties do you need to define a state? 2 properties to define a state. And remember, when you are under the dome, if you are under the dome, can you have pressure and temperature be the 2 properties? It's one or the other. You cannot have both of them because they are dependent. Remember, that has to be 2 independent properties. When you are inside the dome, remember column number 2 and column number 3 of table A2 and A3, for each temperature there is a there is a saturation pressure, and for each pressure there is a saturation temperature. So if you are inside the dome here, then you can either use pressure and maybe specific volume, or temperature and specific volume, but you cannot use pressure and temperature. But outside you can use both.
I have
Yes.
a question about quality.
Yes.
If it's expressed as a percentage, right?
No,
Or well, a fraction of 1.
it's a fraction of 1.
Okay. So is that proportional to its position on that line between?
Yes.
Okay.
Yes.
So like if 50.5 is exactly halfway between the saturated liquid line and the saturated vapor line, or
Well, not quite. I tell you why. Because X is defined as what? Mass of the vapor divided by the total mass.
right?
So you cannot be exactly in the middle
Okay.
because the density of the vapor is not the
Okay,
same
right,
thing
right,
as the
right.
density of water, right? But the only thing you can tell is that all this line in here, x
Yeah.
is equal to, for the saturated liquid, what is the value of x?
0.
0.
Okay.
And then here, x is
1.
1.
Only reason I ask is just for like the visual representation.
Yeah,
where the
visual
dot is.
representation, that line is pretty
It's blurry.
blurry,
Yeah,
yes.
okay.
It doesn't mean you have to be exactly in the
okay.
middle or something like that. So, pure substance, single phase, so I'm gonna skip all this. Remember, single phase here, two phase here, single phase back there. Saturation state, where phase here, the vapor state, the vapor starts, right? And here the vapor, 100% vapor. The dome shaped, we already talked about this, saturated liquid, saturated vapor. Here is the critical temperature and critical pressure. Remember, when you have this, obviously, one thing that's missing in here is the pressure lines, right? As you go from below to up, you know, the pressure goes up. And a quick example here, if you have 100 degrees, right? Remember the value that corresponds to the liquid is called F in the tables, has subscript F, the other one has subscript G, and that's all we really need to know for this stuff. Let's see. So this region is called the liquid or the subcooled liquid or the compressed liquid state. The F is associated with this, the G is associated with that. And then, again, as I just indicated a moment ago, the quality is defined as mass of the vapor plus divided by mass liquid plus mass of vapor, and it changes from a value of 0 and goes to a value of 1. Retrieving thermodynamic properties, obviously, there's no, we learned how to use them. I think we've kind of practiced many times. And you're gonna be using them now more often because that's the only way you can figure out what's going on. So we'll come back as we look at some examples how to use those tables again. And one of the things that is important that is very, that you have to do most of the time is interpolate, because you will never fall on a temperature or on a value that gives you an exact stuff, and linear interpolation is the way to go. Okay. And then how do we use X? Obviously, the value of V is always equal to the value here inside is the value here at F plus X times the value of G minus the value of F, whether you're talking about specific volume or you're talking about internal energy or enthalpy or entropy. Okay, so we talked about those, and then we finished with ideal gases. Remember, the equation is PV is equal to RT, and we used this many times. When we use water vapor, we're pretty clear. You know, we can have tables for this, but you cannot have tables for air if you are given a pressure, right, and a temperature, because it depends, you know, what specific volume you have. So for air, we use what we call the ideal gas equation, in which the pressure times the specific volume is equal to R times T, right? And that was the end of chapter 3. So after doing 3, then we moved on and said, okay, we know everything now about a closed system, right? Then we moved on and talked about open systems. What if you have an opening in your, now for an open system, for a closed system, we only had to worry about conservation of energy. That's what the first law is, right? But when you have an open system, what else do you have to worry about? Conservation of mass. Did we have to worry about conservation of mass with closed system? No. Whatever mass you had is If I have in a gas cylinder, I have 1.5 kilograms of air, that's how much is going to be there, whether that thing is expanding or contracting, right? Or compressing, I should say. But when you have an open systems, well, I have maybe 5 kilograms inside. I don't know how much is coming in, I don't know how much is going out. If both of them are the same, that the mass still is the same. If what comes in is more than what goes out, I have a buildup of a mass, right? Otherwise, I have a depletion of the mass. So when you talk about control volume, because it's no longer control mass, it's control volume. Now the volume is the same volume that is there, but you have stuff coming in and stuff going out. So the key equation in here is that the change of the mass of the control volume is the mass in minus the mass out, period. That's a simple equation. And obviously if you have more than one inlet, one exit, you just have to add the summation symbol. So this is how we represent an open system, right? Or a control volume, right? It's just a system that has both a solid boundary and then an inlet and then an exit, right? Now, the interesting thing about this is that at the inlet, it depends what the pressure is in here, what the pressure out is in here. Remember, pressure, as we will see tomorrow in fluids, pressure always, if you give it a boundary, it's whatever acts on the boundary, it pushes on that boundary, okay? That means you have a certain force that comes in here, certain force that goes in there. And one key equation, another very, very important equation that we learned in thermodynamics, which we'll use also in this case, is how is the mass flow rate related to, how is AV called? What is this quantity AV?
This area of flow rate.
It's, so this is area times, not volume, velocity.
Or the volume.
So this is also known as, has a name.
M dot.
No, it's not M dot.
I think it's volume.
Volumetric flow rate.
Or,
Okay, so this is a volumetric flow rate. Why is that? Because, well, area is in meters squared, right? And velocity is in meters per second. So cubic meters per second, that makes sense, right? Volumetric flow rate, so the volume per unit mass, per unit time. But the relationship between that and the mass is that m dot is always equal to rho AV. Because we are in thermal, we don't like rho, we write it as AV over V. Okay, so again, so the conservation of mass can be written in terms of the AV over V in this fashion. And in steady state, dm control volume over dt is 0. If the open system is in steady state, it had 5 kilograms inside, it will always have 5 kilograms inside because it does not change with time. That means that the mass flow rate in, the total mass flow rate in has to always equal the total mass out. So based on this, we went back and said, okay, now how can we change that Q? How do we write the first law of thermodynamics for an open system? Well, first of all, for an open system, we write it in rate form. That means it's per unit mass. Why do we write it in rate form? Is because the mass is coming in rate form, right? Somebody tells you have a system that lets in 2 kilograms per second of air or something like that. That's a rate, okay? So instead of having dE over dt is equal to q dot minus w dot, which would be applicable for a closed system, right? Now what are we adding? What does this represent, you think? What does this term represent?
Energy, right?
Energy that the fluid coming in is bringing in, minus the energy going out, okay? And there you have your first law of thermodynamics for open systems, okay? And that's really the key of chapter number 4 in this case. And then also in chapter number 4, we introduced the concept of enthalpy by combining internal energy. What is the relationship, by the way, between between enthalpy and internal energy? Anyone remembers? H versus U.
PV.
That's right. H is equal to U plus PV, right? So very, very important relationship. That's why that first law of thermodynamics, when you include that P, pressure N times the velocity N, etc., suddenly you have, the H that applies, where H is actually the enthalpy. And then we went ahead and we applied, if you guys remember, we applied this equation to different components, such as a nozzle, a diffuser, and when we did this last term, I said we will look at them next in this class, which we will do later on. And we will simplify, because each one of these, like a nozzle, a diffuser, are all open systems, right? So that equation will actually reduce to almost nothing. With tunnel, so for control volume, here for a nozzle or this, it can reduce to this one. For a turbine, the work done by a turbine, and guess what is the significance of this? The significance of this is that for a turbine, if I know how much mass flow rate is coming through a turbine, and I know the state of my substance at the inlet of the turbine and the state of my substance at the outlet of the turbine, I can figure out what? The work. And then compressors and pumps, kind of the same thing. When you simplify that equation, you find that the work done on the control volume is simply the change in enthalpy. It turns out that this enthalpy is a very, very important property that we're going to be using quite a bit in this class, because the change in enthalpy, as you can tell, tells you exactly what's happening across, how much work, for example, this pump or compressor is using up, right? And heat exchangers, again, some simple modeling there. Throttling devices, we said that the H across is exactly the same. And then system integration that we will be doing here in this class. So this is actually the typical simple vapor power plant that we're going to be doing in chapter 8. Now, all these open systems that we have been studying, we will use parts of them, usually in fours. Like, you have one of them, second, the third, and fourth. We integrate them to achieve a certain outcome, okay? Like in this case, what we will be doing is converting heated vapor, right, into work, right? But we have to build a system around those, to do that, and that we'll look at that in detail in chapter 8. Okay, that was end of chapter 4. So what did we do in 5? In 5 we talked about second law. Second law of thermodynamics. Again, I'm not going to go into details with this. The crux of the chapter number 5 is that some processes in nature only occur spontaneously in one direction, right? So things lose heat, lose pressure, right? Things fall, from high potential energy to low potential energy normally. That doesn't mean that you cannot throw them the other way, but if you want to do the other way, you have to intervene, okay? So, and the big question behind studying the second law is that if there are some spontaneous stuff that's happening in real life, right, in nature, even though going the other way, like from right to left for those, even though you can conserve energy, you can't tell, if something is happening in this direction, left to right or right to left. In other words, people have recognized, thermodynamicists have recognized that the first law by itself is not enough. I mean, it's conservation of energy, which could go either way, right? But it can't tell me if a process can happen spontaneously or not, okay? Hence the idea of doing the second law. Now, the second law, by looking at this, we said, okay, if there is some spontaneous work that's being done, what is the maximum amount of work I could get, and what could preclude it from getting that big value? Obviously, there are inefficiencies and all that kind of stuff that happen. So we moved on and said, okay, let's look at those statements of the second law. Remember, we talked about 3 statements. The first one was the Clausius statement. The second one was the Kelvin-Planck. Kelvin-Planck, if you recall, was only applicable to cycles, right? And then there is the entropy statement. The first one is the Clausius statement, which says that it is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hot body. It kind of makes sense, all right? Because we know that heat spontaneously flows from hot to cold, right? But from cold to hot, no way, you know? You've got to have something else. It cannot be the sole result. Something else has to happen. So that's the first one. Thermal reservoir, we define the thermal reservoir, what it is. You don't add or remove heat, the temperature stays the same. And then we moved on to Kelvin-Planck statement, the second one, which says that it is impossible for a system to operate in thermodynamic cycle and deliver a net amount of energy by work while receiving energy by heat from a single thermal reservoir. You know, we did this before for a power cycle. For a power cycle, which gets heat from here, right, QH, there is a QC in there, and then there is work, right? So what is the efficiency of this cycle? Is the output divided by the input. Output being W, and the input being QH. So what the second law says is that you cannot have this by communicating with only one reservoir. In other words, if you are communicating with one reservoir, that means that QC is equal to 0, right? If QC is equal to 0, by the way, what is this W equal to? It's QH minus QC. Yeah. So if QC is equal to 0, that means that W is equal to QH. That means that eta is equal to 1. That means this is impossible. Okay? So that's what the Kelvin-Planck statement implies, is that you cannot have something that is 100% efficient. The last statement was the entropy. Remember what the entropy is? The statement of entropy, which we covered in chapter 6, was it is impossible for any system to operate in a way that entropy is destroyed. Remember, there is always entropy production, right? At the worst case is that the entropy production is 0. So it's either 0 or positive, but it cannot be negative. You cannot eat up. It's almost like somebody says, you have friction or frictionless, right? If you have friction, what do you lose? You lose energy, right? If it's frictionless, you don't lose anything, right? But you're not extracting energy from a frictionless thing, okay? Kind of weird analogy, but at least I think it makes sense. One of the important uses of the second law is to determine the best theoretical performance of systems. So here, if it says that you cannot have 100%, okay, if you are telling me you cannot have 100%, how much can I have? Okay, now that depends obviously on what the things that do not allow you to get the maximum is when you have irreversibilities. In other words, friction. Okay, if you don't have those, or if you have those, okay, skipping most of that. Remember, the second law says that W cycle is less or equal than 0. This implies that you cannot produce any work if you are only communicating with one reservoir. Oops. Okay, we mentioned this, thermal efficiency. So again, a corollary is that you cannot have something that is 100% efficient. as I have just shown on the board. Now, when you go to the Kelvin to find out what is the maximum efficiency, then you figure out that the ratios of the heats are actually equal to the ratios of the temperatures of the reservoirs, okay? Remember, the Q's becomes the T's, okay? When you go from when you go to reversible stuff. And hence we get what we call the maximum Carnot efficiency. And we're gonna be talking about this again many times this term. If somebody tells you, okay, you have a power cycle that's operating between 200, 300 Kelvin and 1,000 Kelvin, okay? What's the maximum efficiency can you get? No brainer, right? It's 1 minus, instead of QC, didn't write it there, but instead of 1 minus QC over QH is 1 minus TC over TH. In other words, the only thing you need to know is the temperatures of the reservoirs. That's why in the turbine industry and all these kind of things, people like to increase the efficiency by doing what? By increasing the operating temperatures, the hot operating temperatures. Because clearly, if the temperature between these two is not that big, the temperature difference, let's say I'm operating between 300K and 400K, big deal, you know? You think you're gonna get much efficiency? No, you know? So the closer those two temperatures are, the less efficient you're going to be. If TH is increased, what happens to this ratio? As TH increases, it becomes smaller, so you're subtracting something smaller from 1, that means you're gonna get bigger value. So, and they are only limited by metallurgical stuff. Obviously, they'd like to get as much as possible, but you don't want the blades to to go beyond their melting point or this or that. That's why they do all these cooling within the blades, etc., while they are in the system, just to increase the efficiency. Okay, move on. Power cycle. Okay, and that was really what chapter 6 was all about. Is really just talking about those three things: the spontaneous, and then finishing with a Carnot that tells us what is the maximum efficiency or what is the maximum coefficient of performance. Then we moved on to chapter number 6, which talked about the entropy. And then based on this, we talked about, which I probably didn't have in here in the previous chapter, we started with a Clausius inequality, which is simply the integral over delta Q over T is less or equal than 0, right? But then when it's reversible, it's obviously equal to 0. And then we looked at, applied this to 2 different cycles, you know, AC and BC. And then using the Clausius inequality, we figured out that it doesn't matter. As you go from 1 to 2, this integral always stays the same. That means it's a change in property, right? And that's where the entropy comes in, and therefore the change between here and here is simply S2 minus S1, and therefore the heat is here is joules K, so the unit of SI, unit of entropy is that. Then we moved on and talked about the TDS relations. And again, I'll probably ask this question again. Where does this equation come from? The first TDS equation. It's the first law of thermodynamics. Remember, delta Q minus delta W is equal to delta, well, du, sorry. Why am I using this? Because these are not properties, right? They are dependent upon the path. But if you recall, W is equal to the integral of PdV. That means that delta W is equal to PdV, right? And then we know that delta Q over T is equal to ds. That's the definition of entropy. That means that delta Q is equal to T ds. hence, you're going to have TdS is equal to du plus PdV, okay? And then when you introduce the fact that H is equal to U plus PV, you know, then you can get the second TdS equation, okay? The two of them. And then you can choose either one of them. For example, if the specific volume is constant, to find out, for example, how ds changes, it's probably be a good idea to use this equation because dV is equal to 0, right? But if it's a constant pressure process, it's probably a good idea to use this equation, right? Because dP will be equal to 0. And then based on this, remember the idea after defining entropy is to, in thermodynamics, you're going from one state to another, to another, to another, so you are always seeking changes. How does that property change? In other words, how do I find how entropy changes, okay? If you want to find out how entropy changes, you use the TdS equations, right? Because that's the one that's a differential change in entropy, which after you integrate, you get that. So when we went and talked about incompressible substances, which one of these two equations is probably useful to use? Is it this one, the first, or the second? Incompressible. The first, because specific volume stays the same, okay? So if you do this, then this one it goes to 0. That means that, and then you integrate, you find that S2 minus S1 is simply equal to C specific heat times the log of T2 over T1, you know, direct equation. Now, we don't always deal with just liquid states, sometimes we'll deal with gas states. So how do we find how the thing changes? Well, that means we have to integrate either one of these two equations, you know, to find either this one or this one, you know, to find how the entropy changes. The first one gives you this, the second one gives you that, and then we said that this is a very complex thing to calculate, but thank God it was included in the tables as the S0, right? Okay. That means we are now armed with we can find an entropy change of an incompressible substance and of a compressible substance directly, you know, by using these equations. And then we said that if you have pressure and volume and specific volume or volume plotted, the area under the curve represents work. If you have temperature versus entropy, the area under the curve will have a meaning of, will represent heat. Talked about the Carnot application, and this is that last equation that we talked about, which is the entropy balance. So the entropy change, just like energy change, the entropy change, how do we account for the change, is what gets transferred through the boundary plus whatever gets generated. Whatever gets produced, if you will. The production is always 0 when you have a totally irreversible process. But the moment you have something, an irreversibility, you're going to have some production, okay? And we looked at some examples on how we can evaluate that, and that's really the key equation. And that was for closed system, by the way. If you have an open system, then you have to actually factor in the entropy in and the entropy out for that equation. Lastly, we looked at the ideal gas tables and finding out how P2 and P1 changes as a function of these, and these are functions of the relative pressures, and we will have opportunities to look at these more when we do chapter 9. Okay, so we're going to spend some time with them, and that does it for the review. Let's see here. Just took a little bit more than an hour. Just a quick Review, would you consider the following to be closed, open, and isolated system? For example, a jet engine, is that open, closed, or open? How about the earth, including its oceans and atmosphere? Yeah. Unless you have a meteor or something like that coming in.
Spacecraft
Yeah.
going out.
Yeah. So let's see, that's open, right? And this is closed. If you ignore, meteorites entering the atmosphere and gas molecules escaping gravity, etc., a kinetic energy of a fastball is 25 joules. Does this statement describe an extensive property, an intensive property, a state, or a process? What do you guess? When somebody says, I have something that has the kinetic energy of the ball is 25 joules,
Mass dependent.
okay?
So
It
it's
can be intensive,
extensive.
and it's not a state or a process.
So it's not a state. Why isn't it not a state? Well, it's not, we're not talking about a state of a substance,
Yeah.
between, this is just an
Thing.
object that has a
Yeah.
certain mass. So it's more, and it's not a process because it's not going from one thing to another. So by proceeding with elimination, it's probably an extensive property. Does that make sense? How about a bike tire is pumped from atmospheric pressure and 70 to final conditions of 70 psi and 90 degrees. Does this statement describe an extensive property, an intensive property, a state, or a process? It's very clear, it's a process, you have two states. So this one is an extensive property and this one is a process. A gaseous propane storage tank heats up in the sun and its pressure rises until it reaches a pressure where the safety relief valve opens. What kind of process does this statement describe? Is it an isobaric, isothermal, isometric, or adiabatic? Let's take a look. What does isobaric mean?
Same
Constant
pressure.
pressure.
So do you think that applies?
No.
What does adiabatic mean?
No heat exchange.
No heat exchange, but what is there heat exchange? How about isothermal?
Same
Same.
temperature.
Do you think it applies in here?
No.
Why? Because
Heating up.
yeah. So isometric,
Possible.
constant volume. Okay. Chemists like to call this an isochoric, CHORC.
Why do they have to go make things different?
Yeah, I know, it's crazy.
Chemist.
So isometric, engineers like to use that. Fundamentals of units, times length, etc. Times second foot. Notice that most people in the United States are familiar with describing their weight in pounds, and many have never heard of the unit pound mass. Are they the same? No. That's right, one of them is the mass, the unit of weight, and the other one is the unit of mass, and we know that weight is equal to mass times the acceleration of gravity.
Isn't the unit of mass a slug, actually, not pound mass?
Well, depends on the units. Some places, they call them slugs, you're right. As we will
Which is
see.
what, 32 pound mass
Yes.
slug.
Yeah. 32, when you talk about a slug and talk about the pound force of one slug, it's like taking the weight and dividing it by 32.2 to get the mass in slugs. Yeah. That's why I like SI. Never have to deal with this stuff. So at the beginning of a process, the thermometer reads 15, and you want to stop the experiment when the absolute temperature has doubled. What is the final temperature in degrees Celsius? You don't want to not waste time, but so what do? So you convert this to Kelvin. Yeah. I mean, there are different ways of doing this. Maybe I could have converted this to Rankine, maybe by adding 460, right? And then multiply by 2, and then subtract again 460, get the final temperature in Fahrenheit, which converts back to Celsius. Or maybe the easier way is to take the initial temperature here, 15 degrees, and convert this to, like the way it's done in here, it's in Celsius, minus 9.4, which in turn is converted to Kelvin. Now you're doubling the Kelvin, right? Which is 254, because it says what is the final temperature in degrees? C. Here you find 526.7 minus 273, that gives you 254.4. So you check the pressure inside a flat tire using a standard tire pressure gauge, and the gauge reads 0 degrees. Is there really a vacuum inside the tire?
No.
Okay. So that means that you are just at atmospheric pressure, because it's a gauge pressure. Okay. What is this? After fixing the tire, you inflate it to 30 psi, as recommended by the tire manufacturer. What is the absolute pressure inside the tire?
44.7.
That's right. So, so this is the gauge pressure. You know, to find the absolute, you just need to add the atmospheric pressure, and therefore it's 44.7. What is this? How much work is done by a person holding a box in place on an incline? Zero?
It's not moving.
Because there is no motion, exactly.
Yeah.
You know, it's like a trick thing. You know, there is force. I mean, he is pushing on the thing, but if there is no movement, remember, force times distance. The box ain't moving, right? So there's no work. Since work is the integral of f and the box does not move, ds is 0, and no work is done. There you are. Air contained within a piston cylinder assembly is slowly heated, as shown in the figure below. During this process, the pressure first varies linearly with the volume and then remains constant. So it's a two process, right? Process 1 and 2, 2 to 3. Question, what is the total work done? Imagine you had this. Now, how would you do it? Hint.
Work is gonna happen between 2 and 3.
What's that?
I said the work is gonna happen between 2 and 3, right? That's where we have the volume change.
We don't have volume change between 1 and 2?
Oh, no, I guess we do.
Yeah.
Yeah.
Work is equal to.
Well, hint.
So you're
You have a plot of pressure versus volume.
Area under the
Area.
curve.
Area under the curve, darn. Come on. Area under the curve. So it's this area plus this area. You don't need to remember any equation or any stuff, okay? Significance of a PV diagram is very important. So it's this area plus that area, you know, it's easy to calculate what those areas are. And then you can get your work. I'm not gonna do this. You guys remember this. Q minus W equals delta E. Remember, delta E is the final minus initial. As long as we don't make that thing, we should be fine. A closed system consists of a two-phase liquid vapor H2 in equilibrium at 30 Fahrenheit. The quality is 0.8 and the mass of saturated vapor is 2 pounds. Determine the mass of saturated liquid. So you have something that's within the dome. You know what the temperature is. This temperature will allow you to find what?
Your saturation points, right?
Yeah, so it gives you so you can find the VF and the VG.
Mm-hmm.
And because you know X, what can you find? You can find the V at that particular location, right? Where that V, where the, but what you are being asked is really what is the mass, not the V, okay? So, well, because I need to move on. Definition of quality is mass of the vapor divided by the total mass, right? And what I'm being asked to find in this particular case is really the mass of saturated liquid. Because eventually I'm going to have part of it is liquid, part of it is mass, and I'm being asked, oh, what is that mass of the liquid portion? So I have to use my equations because this is my mixture, right? It's saturated liquid at 0.8. So to find what, using the definition of quality, the quality is equal to, what's right here? Mass of the vapor, which he calls here mg, divided by mg times m of the liquid, right? So when you look at an equation like this and you want to find what mf is, right? So you can say that mg is equal to x mg plus x mf, right? Based on this, you can find what mf is, right? Which is simply equal to mg minus x mg divided by x, or simply mg times 1 minus x over x. Okay, that's where that equation comes from. mf is equal to 1 minus x over x times mg, right? But mg is already given, right? It's 2 pounds, so you get 0.5 pounds. So this is the mass of the liquid. The total mass now is, you can add both masses, you know, to find its the total mass inside is equal to 2.5 because mg was already given. And then using the data from table from there, and we can find what V is. Remember, VF and VG can be found just by using the saturation temperature of 300. So you find that it's 5.18 this. So V is equal to simply M times little v, which gives you 12.95 cubic feet. All right, and I think I'm going to skip this one. Okay, that kind of concludes the review, which I hope has been a little bit useful.
Are you gonna put that?
I already
on the
did.
thing? It's already on there?
Yeah,
Okay.
yeah, I did those yesterday, so. So let's take a little 5-minute breather here, and then we'll start tackling.
Wow. See it on my book.
I did it like around 10.
Yeah, it was there yesterday. Well, it's a big stage.
I saw it on outrage.
Do you have our final exam?
I have them, but I have them at home. Didn't bring them.
Do we
Do
get
you
to
need
see them
them?
or no?
I just
You
wanna
wanna see them?
how yeah.
Okay, I'll bring them next time. For your viewing pleasure, as long as I can keep
Viewing
them.
party.
Yeah.
Pleasure.
How did, you grew up here?
So we were laughing earlier because I'm going through the text, right? And I ran into this nice little quip about, come on, okay. E,
That one.
that,
Oh, I was gonna
Yeah.
mention something about that.
and I'm just sitting here going, I'm like,
There is
man,
going to be an
read that.
interesting thing. You
Yes,
see, they use a different font.
yes.
That's a key.
Uh-huh.
They use a different font, and I go like,
It's like,
why? Why didn't you
seriously?
just put another X in it?
I
You know,
know.
like E sub X or something.
Yeah, I started putting E sub X
You know.
on stuff, so.
Yeah, that can throw you off.
I was like, kidding me.
What other classes you take?
That tiny little note. If you didn't even
Vibrations.
see that,
Oh.
take
Yeah.
it.
Senior
Yeah.
project.
Oh, okay.
So, what about you?
I was looking over here, I was like,
fluids mechanics
that's
and
funny. That's
machine
a
design.
different
Oh,
font.
wow.
I was like,
Yes.
why is that? And I
One
didn't read it in
thing
here.
That'll be a
and then I
full
was like,
load.
wait a
I know,
second.
yeah, it's crazy.
How many
Yeah.
Qs do we need?
How many V's do we need? How many V's?
How many Vs do we
There you
need?
go.
So when you graduate,
But yeah, so.
Some of us
Yeah.
Hoping after summer quarter.
oh,
So that's the plan. See how it turns out.
You done with your project, Scott?
No, I'm in the middle of it.
How's it going?
Pretty good. Yeah, had a pretty good head start during the summer. Working ahead on it.
You got the injection molding machine done?
Yeah. There's another group doing like a really, really fancy injection molding machine for theirs. Like mine's just it heats it and I pull a crank and it, injects plastic. Yeah.
Yeah.
I'm really interested to see what they come up with.
Yeah.
This sounds like a lot.
What are they doing for their machine? What are they doing?
Well, they're like designing an injection molding machine that has like a pneumatic device for injecting, and they have a clamping device and stuff, and they're gonna have to create their own controller for it and stuff. And I just found design off the internet and built it from scratch. So it's not quite as in depth as theirs is gonna be, but their whole project is the machine, where clients kind of more of
The end product?
the process and the product I'm trying to make. So
Building their own seeds and 3D printer. And I was like, Freak.
Build your own 3D printer, your controlled 3D printer.
Or
Is your project changing? Is that what you're saying?
a caffeinated vending machine.
I think the
Or
3D,
the lab.
I think the 3D printer is gonna be easier, but
I was watching a thing on how to do a vending machine, so.
excellent, how to make your own vending machine.
that'd be kind of fun.
Caffeinated. One of those like in Costco where you get the coffee, yeah. I forget what they're called. It starts with U or something.
Where the cup drops down.
Yeah.
Yeah,
There's
that's
one
cool.
at some other Costco, and then there's some at like Edmonds Community College and a couple other places. But yeah. Or just a vending machine filled with monster nuts.
It's a chocolate covered disposable means.
That too. Make a vending machine. Okay. Powered by.
machine that if you don't, then something that's already packaged, you gotta deal with the cleanup.
Yes.
You have to design it to come apart and be cleaned. It says what? And not provide them a way to disassemble the machine so that you can
Figure it out, machine design project.
You know how lazy students are.
All right, guys.
Computer break.
We're gonna see if we're going something.
Yeah. You gonna bring a snack?
Oh, yeah. Well, I have lunch so early. And I think I just wanna yeah, I don't think it's
All right. So let's start with
Before I go to the gym.
the exergy chapter number 7. So let's start with first the objectives of this chapter. We know from Thermo that we have conservation of mass, we have conservation of energy, and we know that we have the second law of thermodynamics. In other words, there are some processes that only occur in a certain way. Okay? So we will introduce the exergy analysis based on this. And the importance of developing this is as follows. Most of the concepts, if you recall, the second law of thermodynamics tells you that you cannot have something that is 100% efficient, meaning that you always have to dump some energy. Okay. So that means you have to dump some energy out into the atmosphere or something, okay? And that energy has some value, okay? What if you could tap into it to use it somewhere else, okay? Like for example, we'll look at some other examples in just a second. In other words, the energy that is about to be lost into the atmosphere, it's a thermal energy, for example, right? It's got a certain value. And the question is, the moment it starts and dissipates into the atmosphere, that's it. It's gone. You can never recuperate that, right? But in the beginning, if you could have a way of harnessing that, you could use it for something else. So it's the same amount of energy, but in the beginning it has some value. At the end, it has no value, okay? I think the example that is in the book kind of gives you a good indication of that. So we will actually talk about the first 5 sections in here. We will introduce the exergy, we will conceptualize it, and then how do we calculate it? That's the more important one. There is only one key equation in this whole chapter, by the way. You know? So it's this. It's really how do we evaluate the exergy of a system? How do we do a closed system exergy balance and the exergy rate for control volumes, because we don't always have closed systems. Sometimes we do have open systems too. So let's introduce the exergy, okay? We know that energy is conserved. This is the key word, conserved. Energy is conserved in every device or process. It cannot be destroyed. It just changes form from one form to another, okay? So energy is there. Energy entering a system with fuel, electricity, flowing stream of matter. Now think of a system as just, you have to kind of visualize something in which something is coming in as either fuel, electricity, flowing streams of matter, and so on can be accounted for in the products and byproducts. So if energy comes in, you got 1,000 joules, you better account for 1,000 joules of the other, when you do the accounting. Maybe 500 went there, 200 went there, etc., but 1,000 has to start. However, the energy conservation idea alone is inadequate for depicting some important aspects of resource utilization. We'll come back to this in just a sec. Look at this very interesting example, which is typically used in most textbooks to illustrate the concept of exergy. Imagine here you have what we call an isolated system. Okay, what does it mean, isolated? That means it does not communicate through heat or work with the outside, right? Based on our knowledge of this, what's the energy of the system is? It's not zero. It stays the same. It stays constant, right? Now imagine that within your system, this big system like this, what you will typically have is a fuel source, right, with a flame. And then you ignite the flame. So your system, the air surrounding this is originally at a temperature Ti, right? And then as time goes by, what's going to happen? Well, the fuel gets depleted, and then when the fuel ends, what happens to the flame? It goes away, right? Now, what is the amount of energy here in A compared to the amount of energy in C?
Same.
It's exactly the same.
Trick question.
Now, but which one, if I were to tell you, okay, now, I'll give you this, which one would you choose between the two if you wanted to do something with that energy? Would you choose the first one or the last one? The first one. Why? Because you got a flame that's going on there that you could use for something. Here, at the end, what you have is just maybe the air here, temperature has probably gone up a little bit. Big deal. If it's like 23 degrees versus 24 degrees, so it's a little warmer, right? But I cannot do much with this, okay? So even though the energy is the same, you guys have recognized that the value here is more important, right? This has more value, so that's where the exergy comes in, okay? So fuel present initially, so the system has a greater potential for use initially than it has finally, okay? The initial potential is largely destroyed because of the irreversible nature of the process, because when you burn something, it's obviously irreversible, just like a spontaneous process is irreversible. So what's causing this energy, this value of the energy going from something useful to nothing, is because of irreversibility. You're allowing all this combustion to occur, and therefore the value of your energy, goes down to almost nothing. So the fuel present initially right here has economic value, while the final slightly warm mixture has really little value. Okay, so that's it's not easy to grasp the exergy right away, right? But at least you know that do you think that exergy, by the way, is conserved?
No.
Do you think does the system here have some exergy?
Yes.
Yes.
How about here?
Yes.
Which one do you think has, if you were to choose between A and B, which one would you take?
A.
Why? Because some of that exergy part of that has gone in the fuel that's there, right? So the exergy starts with a high value and then gradually decreases and decreases, right? So it is not conserved, right? As you go towards the base state, that's it. Here, when you go back to equilibrium with the surrounding, that's your step. Going back to those examples, remember that pressurized can that we were talking about? in, what chapter is that? That's
5.
5, whatever that chapter was. Yeah, in which we're doing the second law, right? Remember we said when you create a hole in the thing, what happens? Right? The air is going to come out, right? And if you don't do anything, what's going to happen? The air is going to come out, and that's it. You end up with a can that has less air. It's in equilibrium with the surrounding, right? But if you were to try to create some work out of it, what would you do? Well, maybe you put a little turbine there, right? And that air is going to hit the blades, and I get a shaft that turns. It's not going to turn forever, because eventually that pressure goes to nothing, and therefore I lose it, right? But at least initially I was able to get something, whereas at the end, if I put a turbine next to it, so big deal, it's nothing happening, and there's no air that's coming out. So there is value in the beginning and nothing at the end. So coming back to this, exergy then is the property that quantifies the potential for use. Because energy is conserved, so it's conserved, 1,000, whatever, doesn't tell me much. But what tells you something is that the potential for use of that energy. If the potential is high, that means you have high exergy, and usually it goes down to almost nothing. When the system goes into equilibrium with the surrounding, the exergy goes down to none. So exergy not only can be destroyed by irreversibility, but it can also be transferred to or from systems. Exergy transferred from a system to its surrounding without use is typically, it represents a loss. You know, if it goes through a boundary and you didn't do much with it, it's gone, you know, it's lost. An objective in exergy analysis, so why do people do exergy analysis? People involved in thermodynamics who build these big power producing stations or this or that, they kind of do this type of analysis to kind of figure out, okay, what am I losing this? Can I harness part of it, right? Instead of just, you know, which means you're really increasing the efficiency somehow. An objective of exergy analysis is to identify sites where exergy destruction and losses occur, because you will always have those, and rank them for significance. You know, am I losing 40% here? Maybe only 7% there, so I'm going to really concentrate on this one, right? This allows attention to be centered on aspects of the system that offer the greatest opportunities for cost-effective improvements. That means if I have to redesign, I want to see where I'm losing a lot, you know, try to kind of mitigate those losses. The example, again, in section number 2, conceptualizing exergy, and we did this again in that chapter 5, right, for a system or a body that is initially at a high temperature. If you pull it out to the atmosphere, what is it going to do on its own? Just cool off, right? And then when it reaches the temperature of the atmosphere, then there is no heat. Okay. Now, what's crossing the boundary of the system? It's Q. It's the heat, right? There's no work. But imagine now, instead of just letting this guy cool spontaneously, you know, on its own, maybe I want to kind of take advantage of that heat. And then I go like, I learned from Thermo that I can create a power cycle. A power cycle is the exchange of heat to work, right? Somehow. Because a power cycle operates between two thermal reservoirs, a hot and a cold. This one is the hot, the atmosphere is the cold, so I have something, I have the two reservoirs. So if I put in a power cycle in the middle, this is just a concept obviously, right? In which I feed this heat to it, and obviously I'm going to lose some. Why am I losing some? Here.
Because you always lose some.
Because you always lose some, exactly, because the second law, all right? But at least I get Q minus Q naught is equal to WC, right? I get something that I could maybe use to raise a weight, turn a shaft, or turn a generator, right? Hook up to a generator or whatever, right? But I can only get this power while this thing, because this temperature will be doing what? Will be going down, down and down until it reaches the temperature TO of the atmosphere, in which case I have nothing, right? I put in here a power cycle, but it's not going to do anything because there is, like when you have no voltage, no current, no pressure difference, no flow, etc. So at equilibrium, right, the body, okay, I forgot here. Instead of the body cooling spontaneously, figure below shows that if the heat transfer during cooling is passed to the power cycle that I have here, work WC can be developed while Q naught is discharged to the atmosphere. We understand this. Now, at equilibrium, the body and atmosphere each possess energy. Let's say this guy became in equilibrium with the atmosphere, right? Each possesses energy, but there is no longer any potential for developing work from the two because they are at the same temperature. Work WC here is realized solely because the initial state of the body differs from that of the atmosphere. So now we are getting to something about this exergy. Exergy is not just the state of the system that we are looking at, but what is the equilibrium state it is trying to go to? Okay? Do you agree that the farther you are from the equilibrium state, the more potential for use that you can have?
Yeah.
Right? So the closer you are from there, the less you can have. That means that in the equation for exergy, probably the property of the atmosphere is going to be important. In other words, what is the temperature of the atmosphere? What is the pressure of the atmosphere? I have to be away from those to get the higher exergy. So exergy is the maximum theoretical value of such work. Now, for thermodynamics analysis involving exergy, it is necessary to model the atmosphere just for the reasons we just talked about, right? Because you have a system that is trying to go in equilibrium with the surrounding. So I need to find what is the property of the surrounding just to kind of quantify what is the value of this energy that my system has. The resulting model is called the exergy reference environment, or simply the environment. The environment is regarded to be a simple compressible system that is large in extent and uniform at temperature T naught and pressure P naught. So usually, unless given otherwise, the P naught is usually 1 atmosphere and the temperature is 25 degrees. Okay, so when a system of interest is at T naught and P naught and at rest to the environment, we say that the system is at the dead state. That means, it changed such that its temperature has reached the temperature of the environment and the pressure of the environment. That means it died. It's at a dead state, okay? At the dead state, there can be no interaction between the system and the environment. That's it. It's in equilibrium with it. So it cannot generate anything from it. Thus, no potential for developing work. That means that exergy at that point is nil. All right. Going on here with a definition. So exergy then is the maximum theoretical work obtainable from an overall system consisting of a system and the environment. So in other words, in order to compute the potential or the exergy of a system, what do you need to know? You need to know the properties of the environment. By itself is meaningless. What is it trying to become in equilibrium with? That kind of testifies as to how far you are from it. The system, so interactions between the system and the environment may involve auxiliary devices such as power cycle that, at least in principle, allow the realization of work. As you put that in between, that's what you get. So we'll come back here to how do we evaluate this exergy. Now that we know what it means, it's just really the economic value of the energy, And we know that it depends on the environment, and we know that the environment is described by a temperature, T naught, and a pressure, P naught. So here's the equation, right there. The exergy of a system, E, by the way, in your book, just so you don't get confused, the book has this E with a different font than this E here. Okay? So I don't know why they didn't use EX or something like that, you know, which I would have used E sub X or E, something like that. So this is exergy. It's in that font, that means it's exergy. And notice what it is equal to. It's the internal energy minus the internal energy of the dead state plus pressure of the dead state times the volume minus the volume at the dead state minus T naught okay, S minus S0 plus the kinetic energy plus the potential energy. Okay, so that's kind of the big equation. And you can probably guess that this equation is extensive because you get the capital letters. Okay, so I'm just going to write it down in here. Exergy is equal to U minus U naught plus P naught, P minus V naught minus T naught, S minus S naught plus KE plus PE. So this is how we evaluate this. U naught, V naught, S naught are the internal energy, the volume, and entropy relatively at the of the system when at the dead state. So in other words, to compute the exergy of the system, it's essentially identifying the system and most likely read some tables, you know, to figure out what is U naught at two temperatures, at two pressures, etc. That's section number 3. So exergy then is the maximum theoretical value of the work obtainable as the system comes into the equilibrium with the environment, i.e. as the system passes to the dead state. So you have a closed system here, heat and work interaction, so this is the closed environment, right? So this is the amount of work that you would get. Obviously, exergy is the maximum theoretical, right? And usually you get that right at the beginning, period, because that's if it's spontaneously trying to go down to the environment, right? The beginning is where it's farther away from the environment, and therefore that's where you could theoretically get the maximum amount of work. So this is an overall system. An overall system is the system plus the environment that's surrounding it. And some aspects of exergy, it's a measure of the departure of the state of a system from that of the environment. So in other words, if my environment is right here at P naught and T naught, right? And I'm at this state right here, so this is the exergy, right? And this state is called the dead state. Let's say I'm going kind of like this, right? The exergy is high in the beginning, and then decreases as you go towards the stuff. And this equation actually gives you my value of U. So the value of the exergy cannot be negative. So it's either 0 or something, because when it gets to this state, right, U and U naught are the same. So this is 0, V and V naught is the same, that's 0, SS naught is the same. It's in equilibrium, so kinetic energy, potential energy changes 0. Exergy is not conserved, but it is destroyed by irreversibilities. So that's why always remember that flame. The value is really high in the beginning, and then as it burns, it's, it's an irreversible process, and the irreversibility is destroying that exergy. Exergy can be regarded as the magnitude of the minimum theoretical work required to bring the system from the dead state to a given state. And when the system is at the dead state, it is in thermal and mechanical equilibrium with the environment, and the value of exergy is 0. Okay? Exergy is maximum, right? Farther away from this. Remember, in thermodynamics, we don't like to work with extensive properties. We like to work with intensive properties. That means now we need to have the equivalent equation to this, but in intensive form. So just like capital U is internal energy, little u is typically called what? Specific internal energy. Here it's exergy, so the little e with that funny font is the specific exergy, right? So it's u minus u naught plus p naught little v minus little v naught minus t naught little s minus s naught plus v squared over 2 plus gz. Here what we have done is just did this kinetic energy per unit mass and potential energy per unit mass. Okay, so what is the unit of exergy? Wow, it's just kilojoules per kilograms. You know, just same thing as U, same thing as everything else is indicated there. A quick example here, just so we see how this plays. Imagine you have you want to use the equation that we just talked about, this equation right here, right? And try to figure out the specific exergy of saturated vapor at 120 degrees. Saturated vapor at 120 degrees, having a velocity of 30 meters per second and elevation of 6. If I stopped right here, would it be enough information?
No.
Well, unless I use the default, T naught equals 25 and atmospheric equals to 1, pressure equals to 1 atmosphere. But it's, in most problems you are given those, because it's okay, it's with reference to what? What is your datum, okay? The datum is that you have a temperature of 25 degrees and a pressure of 1 atmosphere, and G is equal to 1.8. So I know that this is the specific exergy. I mean, without even thinking, I'll start just by writing this equation right here. What does U represent? Specific internal energy of my vapor, which is at 120 degrees. Where the heck do I get that value from? Tables. It's 120 degrees. Which state do you think it is at?
Saturated vapor?
It's 1. So it says here, saturated water vapor. So what is the value of U? Which table should I use? Is it A2? Do you think it's A2? Because it's saturated.
Right on the line.
It's right on the line. So is it UF or UG?
G.
So if I go to that table, A2, and I look at the temperature of, let's see, 120 degrees. So what should be the value of U?
25, 29.3.
U, what am I? 25, 29.3. Does everybody see that? Which is right there. If you don't agree, please, this is the time, okay? Where do I get U naught? How do I get U naught? It's 25 degrees. It's just a value at a temperature of 25, and I turn the page back at 25 degrees. What is the value of U? UG, because it's on the saturated vapor line, right? It should be, it's 1 or, okay, I can't see.
4.88.
104.88 is UO. Yeah,
104.88.
So it's UF.
Okay?
Saturated.
Because it's, you know, because now it's, you see it's 25 degrees, it's liquid, saturated liquid. Okay? That's why it goes to 24.88. Okay? Because it's a liquid, you know, at 1 atmosphere, 25 degrees, you know what that state is, right? So, again, it's all in the tables, okay, without doing any of this, and then without even going any further, just like we read the values of U and U naught, you read exactly the value of V and V naught, and the value of S and S naught. The kinetic energy, this velocity is given, so the V squared over 2 can be found, right? And did we have anything about anything else? 30 meters, and elevation was given as 6 meters. Okay, so the potential there. So you got everything, you know, just plug and chug. And this is 500 kilojoules per kilogram of potential, you know, harnessing that you could have. I mean, that's the value, that's the economic value of that energy, of that vapor at that state. But obviously what's going to happen is that this guy is going to go back and be like this, in which case it just mixes with air and then the exergy is 0. So if I don't get something out of it right at this point, that exergy goes down and down and down and down to nothing.
I've got a question. I don't understand the physics of, if you have a sphere, saturated vapor in it,
That's not a sphere.
or this, what is it? System?
That's
or-
just a representation, that's just.
Okay, so whatever it is.
Yeah,
But it's based off of saturated vapor
Yeah.
temperature.
so it's,
If you have it
okay,
at a certain, okay, never mind, I guess I'm answering my question as I talk it out.
yeah.
Because the higher up you take it,
Yeah.
the water has mass, so gravity.
Oh,
Okay, there we
definitely.
go, I just answered my own question. Okay.
Obviously, it's got mass, it's got, any elevation
The-
difference.
The potential
Yeah.
energy of the system
Mhm.
isn't just the vapor inside, it's
Mhm.
the whole kit and caboodle. Okay.
Well, obviously.
Okay.
So this is where we are on this one. For example, another example, just to kind of try to cement the understanding of this. You have, for example, this is another closed system. A cylinder of an internal combustion engine, right here, contains 2450 cubic centimeters of gaseous combustion product at a pressure of 7 bar and a temperature of 867 degrees, just before the exhaust valve opens. Remember the 4-stroke engine, right? So you got the intake, right?
So squeeze me.
And then you squeeze the compression, right? Combustion, which is the power stroke. And then after the power stroke, obviously you end up with just some very hot gases. And then the exhaust valve opens, you reject that, and then the intake valve opens again. And then you're starting the cycle all over again. So at the end, after the combustion has occurred, what do you need to do? You need to throw that away and get a fresh charge of fuel and fresh charge of air, right? Just to do the combustion again. Now that hot air, do you think it has some value? Heck yes, you know,
turbo.
but it's coming out. There you go. So this is what we are trying to kind of visualize, is really how much exergy is in this stuff. Determine the specific exergy of the gas in kilojoules per kilogram. Obviously the dead state is given here to you, which is 1 atmosphere and 25 degrees roughly, 27 degrees, which is just to make life easy, right? So in here, what equation should we use? That's exactly the same equation as before. The only thing we don't have in here is kinetic energy and potential energy. Why? Because the effect of motion can be ignored because we don't have, you know, it's just the gas, you know, that So we come in here, so that means to find what is the exergy, we need to be able to find U minus U naught. And remember, for a gas, the U is only a function of what?
Specific determinant.
Just the temperature. Remember, for a gas, if you know the temperature, right, the ideal gas equation, right, table 822 that you have used many times before. So if you know the initial temperature and the final temperature, you can find what is the 880 and that. In fact, for just to convince you of this, what is the initial temperature? 860. What was it again? 867 plus 273. That should give you what?
1050.
1,040? 867, no. I had a long day. 867, 273, 1140, right? So you go 1140, is there an 1140 here? Yes, there is. On page 854, right? What is the value of U? Do you see 880.35? I hope that's the number, yeah. 880.35. And then you do the same thing for the other temperature and the same stuff. So U can be written directly from there, right? But V, can you read it from the table for air? No. Why? Because you have to use ideal gas equation, right? If you know, remember PV is equal to RT, that means that V is RT divided by P, okay? That's how we calculate P naught minus this. And then also the entropy change, you cannot read it from tables for ideal gas. You have to use one of those equations that we talked about before, namely S naught minus S naught 0 minus R log P over P naught, right? P2 over P1. Once you do this, then you find what is the exergy, which happens to be 368.91 kilojoules per kilogram. Okay, so now a closed system, so again, that's what I meant earlier, is that the equation that we just talked about here is when you have a system, and this is a dead state, and you are trying to figure out what is the exergy of the system with reference to the dead state. Now, if a system is going now from a closed system at any given state can attain new states by various means, including work and heat interactions with its surroundings. So a system can go from one state 1 to state number 2, for example, like this. And let's say this is the dead state, right? So what we are trying to find in here is really the exergy change, okay? The exergy value associated with a new state generally differs from the exergy value of the initial state. If this is the dead state, do you think the exergy at 2 is higher than 1 or less than 1? Or less than the exergy at 1? Which one of these two has the highest exergy? You think it's 1?
2.
See, 1 is closer to the
Sorry.
dead,
Yeah.
right? So as the system goes, as processes occur, the exergy constantly changes for a state, right? So the question is, how can I figure out now what is the exergy 2 minus the exergy 1, as opposed to with respect to the dead state? You see what I'm saying? Reference with respect to the dead state. Now I'm looking just between state 1 and state 2. Now you can take the original equation and play with it and find out that the exergy at 2 minus exergy at 1 depends on the internal energy at 2 minus 1, volume 2 minus 1, this and that and that. In other words, it's taking this for 2 minus 1, canceling out some terms, and this is how you find an exergy change. Okay? Now, schematically speaking, look at this situation in here. What does this point represent? Which is at T naught and
Dead
P
state.
naught. This is the
Dead
dead
state.
state, right? So imagine now, these are lines of constant exergy contours, which doesn't mean much. But imagine that you have
Topography, man.
1 and 2. I have a process in which I go from state 1 to state 2. From state 1 to state 2, what happens to the exergy? Does it increase or decrease? It increases because I'm going away from
The dead state
the dead state. How about if I go from here to here?
decreases.
It decreases. Big deal, right? So exergy change can be illustrated using the figure below, which shows an exergy temperature pressure surface of a gas together with constant exergy contours projected on temperature pressure coordinates. Obviously here, as you go away from the dead, the exergy always increases, but you go the opposite direction of this arrow, that means the exergy decreases. All right. So, closed system exergy balance. Like energy, exergy can be transferred across a boundary of a closed system. Just like energy, which can go either through Q or through this, exergy can be transferred across, and the change in exergy of a system during the process would not necessarily equal to the net exergy transferred, because exergy would be destroyed if irreversibilities were present within the system during the process. Now this equation is kind of looks complicated. Maybe that's the most complicated equation of this. I mean, there are essentially two equations. First one that we looked at earlier, actually three. One of them was the exergy with respect to the dead state. The second equation is the change in exergy between state 1 and state 2. And this one is the exergy system balance. In other words, it's the exergy that gets transferred through heat transfer or through work transfer minus the exergy destruction. Because if you have any destruction, you have now we need to look at each one of those terms. Let me just write this down. So EX2 minus EX1 is equal to integral between 1 and 2, or 1 minus T naught or TB. Anyone can tell me what TB represents?
Temperature from boundary.
Exactly, temperature at the boundary where the heat transfer is actually occurring. Minus P naught, B2 minus B1, and then minus T naught, C, okay? So this is the exergy transfers. And this one is the exergy destruction. And then this is the exergy change. So if we look at all those terms one by one, the first term here, which is right there, represents, on the right-hand side of the balance equation, is associated with the heat transfer, because there is a Q obviously going on to or from the system, and is interpreted as the exergy transfer accompanying heat. Okay? So obviously, if you are adding heat or subtracting heat, right? Obviously that affects the temperature, that affects the stuff, and therefore your exergy will be changing. So you're transferring essentially exergy through the boundary. And so E sub Q, so this represents E sub Q, is the integral between 1 and 2 minus T naught over TB at delta Q, where TB denotes the temperature of the boundary where the heat transfer occurs. And this one is the EW. Okay, so this is the EQ, this is the EW, and obviously this one is the E destroyed. Okay, in other words, EX2 minus exergy1 is equal to E exergy transferred by heat plus or minus exergy transferred by work minus the exergy destruction, and this is called the closed system exergy balance. Okay? Now, to understand how this one will work, so we'll just do this section and then I think we'll stop for today. The change in exergy of closed system can be accounted for in terms of the exergy transfers and the destruction due to irreversibility within the system. Now this ED, the destruction can either be zero or there could be something positive, right? Cannot be a negative, right? It's like entropy production, you know, it's either there or there is nothing. So ED is obviously greater than zero if irreversibilities are present in the system. It is zero if it is that. Now, exergy destruction is not a property, whereas exergy is a property. So exergy E2 minus E1 could be, so the exergy could be increasing, could be decreasing, or it could be equal to zero. If between state 1 and 2 they are equally distance from the dead state, then E2 minus E1 is zero. If you are going farther, right, or going closer, then you can get either one of these three outcomes. However, if you have an isolated system, remember an isolated system does not have any what? Exchange of heat or work. That means that EQ is zero and EW is zero, and you end up with simply delta E, delta exergy, right, is equal to minus E minus ED, whatever destruction is the negative of whatever has been destroyed. So the exergy balance reduces to give just delta E is equal to that. Let's look at one example here. And again, water initially as saturated liquid, that means on the dome, it's on the left-hand side, right? At 150 is contained within a piston cylinder assembly, okay, no big deal. The water is heated to the corresponding saturated vapor. So how am I moving? And the dome, I'm moving from left to right, horizontally. In an internally reversible process at constant temperature and pressure, okay? For T naught equals 20 degrees and P naught equals 1 bar, ignoring the effect of gravity, etc., determine first what is the change in exergy. Number 2, the exergy transfer accompanying heat and the exergy accompanying work. The exergy, this example is very important. You need to be able to do a problem like this for the first test. All right? Just have to calculate this and that and that and that. Okay?
The first one, we can right off the bat get rid of KE and PE, can we?
Yeah,
Yeah.
right from the get-go. So really, you know, EX2 minus for the exergy change, the equations, you have them, right? You know that I'm going from this state to this state, right? And this is my thing. So I'm coming in for the first one. What is E2 minus E1? Remember, it's U2 minus U1 plus P naught, P2 minus V1 minus T naught, S2 minus S1. What we have neglected is KE2 minus AQ1 plus PE2 minus PE1, okay? Now all I need to do is just to evaluate what is my internal energy at this state minus that state, specific volume from there to, would that be a difficult thing to find? Hopefully not, right? At this stage, we know for what state, the first state that we have, in fact this is from example 6.1, at that temperature. Once you know the temperature, you essentially know what? You know what the saturation pressure is, and you know what UF is, what UG is, you know what SF is, what CUV, etc. Okay? And in fact, they are written right here. Okay? So if you are unsure, you can go back to the tables and make sure that these values are really what you have. Now you can plug in those values, right? And then you find that it's 502.38 kilojoules per kilogram. That's the exergy change from state 2 to state 1. That means that state 2 obviously has a higher exergy than state number 1. Okay? Which kind of makes sense because you're going from saturated liquid to saturated vapor, right? Noting that the temperature, and the second equation is what is the exergy exchange by heat. And then you go like, well, I'm just going to use this equation. 1 minus T naught over T Q over M, right? But what is Q over M? Equal to, well, Q over M from, darn, I think we're given from here, from right there. This is from example 6.1. How do you find this? Is obviously using the first law of thermodynamics, right? To find what is Q, what is W, right? So that's no big deal. But this is what Q is, what W is. So you plug in, you have Q over M right here, and you have 1, you have T naught, and you have T. So it's really just to plug those values and you find that. And then what is the thing by work? Thing by work is W, which is already given there, minus P naught times V2 minus V1, right? And then you should be getting something like 142.71. And lastly, what is ED? Well, ED is no big deal because if you know this, EX2 minus EX1, you know EQ, you know EW. Can you find out what ED is? Yes, you know one equation, one unknown, which is simply minus E2 minus E1 plus EQ over M minus EW over M. And then E happens to be, in this case, that E destruction is equal to 0. That means that there was no irreversibility in the system. Okay? Now, see how many slides do I have? Oh, it's too many. You know, I'm still going to stop right here, 6:30. So we'll finish this next week. You know, so we'll finish this next week, and then we'll pick up the vapor power cycle right after that. Chapter 8. Yes.
Will you put chapter 8 in?
Yes. Yes. Please look at chapter 8 because that's one of the most important chapters of
Is that like
this.
the chapter 3 of this quarter?
Kind of. That's where you learn all that stuff, you know, that's going on. You know. So it helps.
Don't skip class to watch the national championship. I do not. Just kidding. I don't even like watching sports.